Assalamu alaikum, dear viewer. This is Dr. Aisha Nazuk once again with necessary concepts of statistics. Uh, if you have still not subscribed to the channel, kindly do so that you will keep receiving important notifications about the video that I keep on posting. This channel is all about knowledge sharing, about statistics, econometrics, and positive thinking, and even one playlist is on humor genre, so you can explore the different playlists on this channel. And I can keep on posting videos on demand here for the general viewers who want to understand miscellaneous concepts of statistics and econometrics. Those of you who want to brush up basic skills, this is one of the important videos. So today's topic is sampling distribution. Okay, so what is sampling, first of all? As we all know that if we have a complete population, right? We have a complete population and we want to select a random sample from that population. For example, consider in mind that this population is not necessarily population of a country. It could be a number of students in a class, total students in a class, or it could be total chairs in a class. So it all depends what is your item or sample of entity of interest. So for example, if we have a population, let's say my research interests are to analyze, for example, the intelligence quotient or the IQ of a student sitting in a particular class. So my population is all students sitting in that class, right? And let's say I want to select a random sample of, let's say, 5 students. So based on the data of those 5 students, I want to infer or I want to conclude about the average IQ of the entire class, right? So what has this definition to do with sampling distribution is that actually uh, if we theoretically do repeated sampling, I have focused on the word theoretical because in real or in practical life, we never do repeated sampling. We just take one random sample, for example. And as the lecture proceeds, you will get yourself acquainted more with the terminology of repeated sampling. For the time being, what you should understand by now, the content cover that a population is a complete list of entities about which you want to give some results. And a sample is a random and a representative part of that population. Okay, so what is a parameter? For example, as I said that if my research interests are to um, conclude about the average IQ, then my population parameter, or I can simply say parameter, is the average IQ, right? And generally, when we say average, we generally refer to arithmetic mean. If, of course, you have studied different type of averages. So depending upon what type of data it is, you can use the relevant average. But in general, I can say that in this problem or in this scenario, the parameter is the average. Now, what is a sample statistic or simply statistic? It's not necessary that I write sample word with it. So whenever I read the word statistic, I should know that this is something that has been calculated from a random sample. For example, in this scenario where I was discussing that I want to infer about the IQ of the entire class and I take a random sample of 5 students. So if I calculate the average IQ of those 5 students, that was a sample, then that average will be called statistic, right? Because it is calculated from the sample. So simple definition is, if a summary value that describes the data, like the mean, if that summary value is calculated from the sample, then it is statistic. But if that summary value is about complete population, then it is called parameter. For example, in this scenario, the average IQ of the entire class can be called the parameter that we want to estimate, right? We are not interviewing or we are not measuring the IQ of each and every student. We want to estimate the parameter, which is the average IQ of the entire class. And the average IQ of the 5 students that we selected at random, that average IQ is called statistic, right? Because it is coming out of a random sample. So by now you know that since we are doing sampling, so population parameter is actually unknown. In other words, its value is unknown, right? For example, average IQ of the entire class is unknown. That's why I want to estimate. Had this been known, why would I rely on a random sample? For example, another example, if you already know the poverty level in a country, and that estimate or that value is from very recent census, full population census. So why would you go for a random sample then? You will simply use that parameter, right? So sampling distribution or sampling is a concept when population parameters are unknown, right? Okay, so you know that every sample has different observed values. What does that mean? Don't get confused by the words. I'm just saying, for example, in the example of the student selection scenario, if I select 5 students at random, and let's say another teacher enters the class and she also selects for the same purpose 5 students randomly. So her sample will be different and mine will be different. So if we both calculate average IQ, of course, our results may be different. I mean, by chance they could be same, but the final value will be different. Average IQ. That is, if we do repeated sampling, the sample statistic, which in this case is sample mean, or the sample statistic will be different from sample to sample. So what does that mean? This means that we need to know the pattern or the sampling distribution of sample mean or any statistic. So let me read this definition once and then I will give you a better or another interpretation. So sampling distribution of sample mean is the probability distribution of the sample means obtained from all the possible samples of the same size. Now what does that mean? First of all, you have to keep in mind that the word used here is sample mean. But keep in mind sampling distribution can be of any statistic. Like you can construct sampling distribution of sample variance, you can construct sampling distribution of sample minimum and so on. So you could construct sampling distribution of any statistic. But since now in this course we'll be focusing on the sampling distribution of sample mean only, that's why the definition says that the sampling distribution of sample mean is the probability distribution. And what do we mean by probability distribution? That we will have a particular probability assigned to each value of the sample mean. For example, there are 0.6 chances or the 0.6 probability that the sample mean is going to be 2. So how to construct it, I will explain through a numerical example. And this probability distribution is constructed by using all possible samples, right? So I will also explain how to select all possible samples from the population. Okay, so let's have a numerical example here, how to develop sampling distribution. Suppose that we have data on years of experience of 6 employees as follows, right? And let's say this is a case of a very small population. So this list of 6 employees is your population. In general, keep in mind that the population is unknown and the sole purpose of explaining this particular example relevant to sampling distribution is to let you understand the theoretical concept because sampling distribution, keep in mind, is a theoretical concept. And why do we study it? You will understand later when you do hypothesis testing later. Not necessarily in introductory statistics course, but later on when you will be exploring the courses of probability theory or econometrics, then you will be doing or covering hypothesis testing. So at that time, you should know what is the sampling distribution of a statistic. So here I'm going to explain through a given list of population. So suppose this is the population. If I calculate the mean of this population, which you know that the Greek symbol mu is used to denote population mean. So mu is simply add all the values, divide by number of value, and we get 6.5. Then population standard deviation, once again by Greek symbol sigma. This is equal to each value minus mu square, right? So we are subtracting the mean from each value, squaring it up, and then summing, and then divided by number of observation. So this is because population data, so we are dividing by n, not by n minus 1, right? Okay, so now we have the value of mu and sigma. And why we calculated this, you will understand a little bit further in this video. So let's say I want to see that how many possible random samples of size 2 I can select. Keep in mind that even from exam point of view or from conceptual point of view, you should know the sample size. So it is given that the sample size is 2. So how many random sample I can draw if I allow for repetitions in the sample, right? I use the word that I'm allowing repetitions in the sample. So we call it simple random sampling with replacement, right? So if I have to draw simple random sampling based random samples of size 2, simple random sampling with replacement, and sample size is 2. So what I will do is I will note the number of values in the population, which you can see it is 6. So capital N is 6 and small n, which is the sample size, it is 2. So 6 power 2 is 36. So you will have 36 possible random samples. And how to make those random samples? First of all, you start making random samples that start with the entity 2. So since I am allowing for repetition, so 2 will come with 2 ones, then 2 with 4, 2 with 6, 2 with 7, 2 with 9, 2 with 11. So you can see this is the list. Now I will start mentioning the samples that start with 4. Then so 4 with 2, 4 with 4, 4 with 6, 4 with 7, and so on, right? So similarly, I have constructed all possible random samples, some of which will be displayed on the next page. Like, okay, so these one are some of the random sample, remaining ones are here, right? Next, what we have to do is, if our purpose is to construct sampling distribution of arithmetic mean, right? What we are going to do, we are going to calculate arithmetic mean in each sample, right? Like, for example, the first sample is 2 and 2. So the arithmetic mean will be 2 plus 2 divided by 2, which is 2. Then 2 plus 4 divided by 2, which is 3. Similarly, for example, if you see this one, 2 plus 11 is 13 divided by 2 is 6.5. So that's how we construct another column in which we mention the sample mean from all possible random samples. So that's how we have a sort of a complete table of 36 random samples. Now let's say I want to make a sampling distribution. Now what will I do? I will note what is the minimum possible value of sample mean. If you see this table back, the minimum sample mean is 2 and 2 is occurring only once. Similarly, you can see 3 is occurring only twice. So similarly, you will see or you will count the number of occurrence of each value. And then you will have this table, right? 2 is occurring once, 3 is occurring 2. Let me tell you again, how am I counting this? I'm referring back to this table, part of which is here on this page, 52 page, and part of which is here. So I'm noting this X bar column, and I can see 2 is occurring only once, because you can see on the next page there is no X bar, which is 2. So 2 is occurring only once, 3 is occurring twice. Similarly, I count all other values. Then I convert the frequencies into probabilities. So if frequency is 1, so out of 36 times or out of 36 random samples, the probability that the mean will take the value 1 is equal to 1 by 36. Similarly, probability that the random sample will be 3 is 2 by 36, right? So you can calculate all the probabilities, and in the end you can verify that if you add this column, the probability column, the answer will be always 1. Because keep in mind, sum of all probabilities is always equal to 1. Okay, next step. Suppose if your exam question is just that you have to construct the sampling distribution of X bar, then you are done with it, right? Up till now, the table we have constructed, probability form, you are done. But suppose if the question is that you also have to verify that the sample mean is an unbiased estimator of population mean. What am I saying? That if the exam says that you have to verify that the sample mean is an unbiased estimator of population mean, then what you will do? You will calculate the average of X bar. And how will you calculate the average? You just add all the values of X bar, like you have 36 values, right? Here on this table. So just add all the values like 2 plus 3 plus 4 plus 4.5 and so on. Add all the values and divide by total, which is 36. So average comes out to be 6.5. Now how come this verifies that this is an unbiased estimator? If you refer back to the population average mu, you can see that the population average is 6.5. And average of X bar across all possible random samples is also 6.5. So this is what is written in a sort of a technical terminology now, that the expected value of X bar or average of X bar. When I say expected value, that's same as saying the average. So expected value or average of X bar is equal to mu. In other words, what does that mean? It means that on average, the sample mean is converging to its actual or true value in the population, right? That's why we say that sample mean is an unbiased estimator, right? If you are unable to understand what is this unbiased, just come up with something out of statistics. To what type of a person do you call unbiased? If that person has no systematic behavioral errors. For example, if your mother always keeps on scolding you all the time and all the siblings are being pampered, then maybe you have a feeling of indignation that your mother is biased. Why? Because you think this is a systematic error. I mean, she's fine with all other siblings, but with me she has a problem. But what if your mother sometimes scolds you, sometimes pampers you, and similarly to other siblings, sometimes she scolds, sometimes she pampers. So on average, her errors are being, or you could say the behavioral dimensions, they are being balanced out in the long run. So you will say that my mother is unbiased. So similarly, if in the long run, your sample is converging to the population, you're saying this is unbiased behavior, right? So next, I've already explained the concept of expected value. That expected value is simply arithmetic mean. Next, we have the concept of variability in the sample statistic X bar. As I just we've just learned that X bar or the sample statistic is a random variable. And why is it a random variable? Because if you change the sample, the value of X bar changes. So it's a random sample. What if we want to see that what are the expected variation in the values of X bar? If you are not easily comprehending this, coming back to this table where we were listing the values of X bar, you can see that the values of X bar are changing from sample to sample. So what if you want to, calculate the amount of variation in these values of X bar? So that is what we are discussing here. So we can do that through the concept called standard error. So what is standard error? Standard error is basically expected variation in the values of X bar across different random samples. And how to calculate standard error is to simply divide the population variance by the sample size and then square root this. So population variance, if you could see in the beginning, we calculated this sigma, right? So sigma square will be population variance. So sigma square is simply the square of sigma. We divide by sample size, which was 2, and take a square root, and you'll get the value 2.111 something. So what is the interpretation of this standard error? This standard error is actually standard deviation of X bar. Now you would say that you have already studied standard deviation, so why am I focusing particularly about the standard deviation of X bar? Actually, if you have any random variable, for example, if you have your pocket money from the last 6 months, and if you calculate the standard deviation, then it's any arbitrarily random variable, like it could be your pocket money, it could be temperature, anything. So if you calculate the variation, you call it standard deviation. But if you calculate the variation in a statistic, then you call it standard error. That is why we call it standard error of X bar. So one day if someone asks you what is the difference between standard deviation and standard error, you will simply say that variation in any random variable is called standard deviation, whereas variation in a statistic, for example, arithmetic mean, is called standard error. Right? Okay. So next we study a small property of the sample mean X bar. Let's say we define a term or another statistic called z-score. What is the purpose of z-score? It is used to see how much deviated a particular sample mean is from population mean. In other words, you could see X bar minus mu, so deviation between the sample mean and population mean, and you standardize it by the standard error, that is sigma over square root n. And this formula of z is relevant if the sample size is less than or equal to 5% of the population size. But if the sample size is greater than 5% of the population size, then the standard error is given by this formula. So if you are given the population size, you are given the sample size, and I say that you have to calculate the z-score, then what you will do, you will check if your sample size is less than 5% of the population size, then you will use this formula. But if your sample size is greater than 5% of the population size, then you will use this formula of z-score. And an interesting property about z-score, that z-score has a normal distribution with mean 0 and variance 1. And we can mathematically write it using this symbol that z follows normal distribution with mean 0 and variance 1. So whenever we see this notation, you should know that n stands for normal. The first term within the bracket is the mean, and the second term within the bracket is the variance. Okay, so this property, or the z-score being normal, this property holds if the actual distribution of X is normal. Now, what is a normal distribution? I will also make that, I'll help you revise that concept in the later part of this video. For now, what I'm saying that if the actual distribution of the random variable is normal, then z-score follows normal. It means 0, variance 1. But if the sample size is large, then even if the actual distribution is not normally distributed, in an easy word, that even if there are outliers in the actual population, but if your sample size is very large, then the z-score will be distributed normally, irrespective of whether there were outlier in the population, whether the population was non-normal or not. Now, these concepts are making use of the idea of normal distribution. So let's revise what's a normal distribution. It's a symmetric distribution in which values equidistant from the central maximum are same. Don't get distracted by the technical terminology. If you just have a look at this frequency polygon, right, or a graph superimposed on the histogram of the data, if this is a frequency polygon of the X variable and this type of shape is there, this means that this graph cuts the data into, or this line cuts the data into two equal halves. In other words, one half, this half, right? This half is a mirror image of the remaining half. So this is a normal distribution, is a bell-shaped symmetric distribution. And you can see that the values that are equidistant from this mean, for example, if this is the value, then this is the height. Similarly, if I approximately take equidistant value, the height will be same here. That's why the definition. But you can simply define it that normal distribution is a bell-shaped symmetric distribution. So the random variable X theoretically can take on any value between minus infinity to plus infinity. That is a general variation. But it is not necessary that every variable which is normally distributed will take the value from plus infinity to minus infinity. For example, if we discuss that the temperature is normally distributed, of course, we are not assuming that the temperature is varying from minus infinity to plus infinity. We are just saying that the maximum possible range of a normal variable is minus infinity to plus infinity, right? Okay. Now the problem is not all bell-shaped are normally distributed. If you have a look at this data, if the bell is too flat, we call it platycurtic. If the bell is too heighted, we call it leptocurtic. And if the bell is of medium height, we call it mesocurtic. But the problem is, these, irrespective of these terminology, the names, the problem is just by looking at the bell shape, it's very difficult to visually judge what is a flat curve, what is a peak curve, and what is a medium length curve. So we have some formulas through which we can declare whether a data is normal or not. The first thing is skewness. What will the skewness measure? Skewness will check whether the bell shape exists or not, right? Skewness will check whether the data has a bell shape or not. Kurtosis will check whether the height is medium or otherwise. So what is the formula for skewness? The formula is, if you are given a data, just simply first step is find the arithmetic mean, then find the standard deviation, and simply apply this formula, right? I will post an activity sheet on this topic as well for further clarity. So simply, if you are given a list of values, your first step is to find the arithmetic mean of that data and standard deviation of that data, and then a column in which you subtract each value. In fact, you subtract the arithmetic mean from each value and then take its cube. Similarly, in the denominator, we have the cube of standard deviation. So you calculate skewness, and what is the interpretation? That if the data is not normally distributed, skewness will be 0. And if the data is not normally distributed, then skewness will be far away from 0. So in practice, what we say is, if the exact value of 0 is there, then it's a perfect bell shaped. If we have values close to 0, for example, if the values are from minus 0.5 to plus 0.5, we can say, okay, there are some distortions, but we can say that it is close to bell shape, right? Next, we calculate another alternate formula of skewness, right? This is not necessary that you apply both formulas. I mean, if you find that this particular formula is easy using arithmetic mean and standard deviation, it's perfectly all right. Another student might feel that he can easily calculate the quartiles. So, but he can calculate the skewness using the quartiles. And of course, the final answer from both the formulas will be a little bit different. So don't worry about that. But your final conclusion will be same. That is, both coefficients will lead you to same conclusion. For example, if the first formula said that the data is near bell shape, then so does the second formula will say. Although your final result may vary from a little bit, like zero point 0.1 or 0.2. So next we have a formula that measure the peakedness or the height. So kurtosis measure the height, and this is the formula. So simply, you already know how to calculate arithmetic mean and standard deviation. So if you are given a data and you have to find the kurtosis, simply find arithmetic mean, standard deviation, and then find this summation, which is each value minus arithmetic mean raised to the power 4, and then sum it up, and then divide by this number of observation and standard deviation raised to power 4. So if the answer for kurtosis is 3, you could say that the data is normally distributed. If it is close to 3, you will say that it is close to normal distribution. So if when will you comment that a data is normal? When the skewness is 0 and kurtosis is 3. Both conditions should be met. So I will soon post a activity sheet in which we will be calculating skewness and kurtosis in a given data set. Right? Best of luck. If you think that you want to watch this video again, do on in the comment section. You can mention if you have any queries. You can write us an email if you want to further contact us. And those students who are enrolled at NUST for this course, they can all the time contact me through our WhatsApp class group. Thank you.